And what I want to do, which I think is what I've been sort of asked to do, is to give a kind of slightly speculative discussion of what the state of this is maybe now and what we'd like it to be in 10, 20 years' time. So, higher order Fourier analysis is, the central objects of this are things called Gowers norms. So let me first of all introduce what the Gowers norms are, and then I'll say a couple of things about why these are central objects and what they're good for. So fix a parameter k is an integer. You can talk about Gowers norms in various different settings on various different groups, but for most of what I'm going to say today, I'm going to talk about functions supported on some finite segment of the integers, so 1 up to n. So complexes be a function. And then the kth Gowers norm also depends on n, is defined in the following way. So you first of all sum f over k-dimensional parallelepipeds. So maybe what I've written here actually doesn't quite accurately describe what this parallelepiped is. So a two-dimensional parallelepiped is just a parallelogram. And in k dimensions, this will be a product of 2 to the k vertices of a parallelepiped. So you take that, this one may have a complex conjugate over it. Then let's normalize it. So it's going to have size typically on the order of 1. And actually I'll put a normalizing constant here, which I think sort of very mildly depends on n as well, just so that when f is equal to 1, this is exactly equal to 1. So I'll remark on that again in a second. You take that to the power 1 over 2 to the k. So that's the definition. So here C is chosen. So the Gowers norm of the constant function 1 is just exactly 1. In fact, so you'll see sort of minor variants of this in the literature. One other way of defining it is to embed 1 up to n into a cyclic group, define it there, and then sort of unembed, but they're all essentially equivalent. So the most important thing is it's averaging f over the vertices of parallelepipeds. Okay, so why is it considered important? So why is this a central object? Basically, the answer to that is that these Gowers norms control counts of all sorts of yeah. So these Gowers norms control counts of all sorts of objects of interest arithmetically, and the most well-known of those are arithmetic progressions. So they control solutions, so they control counts of linear configurations, of quite general linear configurations. E.g. arithmetic progressions. And just to give you an example of what I mean by control, let me just state the theorem in this line. So e.g. if I take 4 different functions, so f1, f2, f3, and f4, 1 up to n up to the complexes are 4 functions. I'm going to assume these ones are bounded pointwise by 1. lengthwise. So I can write down a kind of weighted count of 4-term progressions, weighted by these functions, 4-term arithmetic progressions. If I normalize so that it's on the scale of 1, then that kind of account will be bounded above by an absolute constant times the Gowers U3 norm in this case of any one of those functions. So this sort of theorem is called a generalized von Neumann theorem. It can be generalized in lots of different ways. So these are 4-term arithmetic progressions that are parameterized here. You could work with k-term arithmetic progressions, in which case you would use the Gowers k-1 norm. And you can also work with much more general linear patterns, not just arithmetic progressions. And then there's also a whole theory of non-linear patterns as well that related things can be applied to. I'm just giving this as an example. So once you have this is not a difficult statement to prove. This is actually just 3 applications of Cauchy-Schwarz. I'm not going to do it, but it's basically once you decide that that's what you want to prove. And then once you have it, it basically lets you can reduce questions about arithmetic progressions, like for example Semiramis theorem or counting progressions in primes, to questions about Gowers norms. So you can use this to reduce questions about APs. So Semiramis theorem, which I'm not going to go into detail of, but probably a lot of people know what that is. Semiramis theorem, APs in primes. To questions about Gowers norms. So another way I sometimes think about this, the Gowers norms are themselves a sort of count of, well, they are a count of linear configurations in a set, or in a function. This particular kind of linear configuration that's a parallelepiped. And so you can sort of think of this as saying that the parallelepipeds are kind of the universal object, I suppose, in this combinatorics of linear equations. So they're the only thing you really need to consider to understand general linear configurations. So what are the questions about Gowers norms that one would like to understand? Well, there's really just one very key question. We would like a way of understanding when the Gowers norm of a function is large. So if we had some way of knowing whether or not this is large, if we could prove it's small, for example, then we can control these averages along, for example, progressions. So that hopefully provides some motivation for what the really key question in the area is. So what can we say about functions f to the complexes, let's say bounded by 1, whose Gowers norm is close to the maximal possible value. So here let's think of delta as some positive quantity. So if we have some sort of an understanding of this situation, suppose we can give a description of functions f with large Gowers norm, and we can try and flip that description and say if we've got some functions that don't have that sort of structure, that the Gowers norms are small, and therefore we can control progressions. So this has sort of emerged as like the main sort of question in the area. So this is called the inverse question for the Gowers norms. Inverse problem. Gowers norms. Any question on that before I start erasing things? What's the preferred border erasing procedure? Should I use a wet cloth or not a wet cloth?
There is
If
you're interested. So it's a two-step process.
I think he's asking for a demonstration.
So wet first and then, yeah.
Yes.
I know there's a high chance of rendering everything completely illegible if I do it wrong. Were there any questions about the general setup? I mean, this is stuff that's been sort of exposited to death almost. Probably a lot of people have heard talks on this basic setup before.
So having small norm for f means some kind of randomness?
Yeah, that's one way to think of it. So one can think of these Gowers norms as encoding a hierarchy of pseudo-randomness. Actually, there's maybe a few things I could just to further orient things, I should make a few comments in that direction. So actually, I haven't even stated, it's not at all obvious that they are norms. So they are norms. And then they're also kind of, they're ordered. Actually, the way I normalize things, that's slightly incorrect, but they are. So saying that the Gowers norm of something is small is some sort of a notion of pseudo-randomness, and this becomes weaker as the norms increase. Okay, so that's the inverse problem for the Gowers norms. If I fix one of those norms, what can I say if the Gowers norm is large? So let me tell you, so there are two basic observations. Two fairly basic observations. So the first observation is that if delta equals 1, then, so that's the maximal possible value that a Gowers norm could be. What you can show is that this happens if and only if f is a polynomial phase of degree k minus 1. So f of x is e to the 2 pi I times phi of x with phi polynomial of degree k. Degree at most k minus 1. And you can more or less see that straight from the definition. So if you first of all, if a function has Gowers norm exactly 1, and if it's bounded pointwise by 1, then since I've normalized things so that the Gowers norm of the constant function 1 is 1, such an f has got to have absolute value 1 everywhere. And so it's got to be e to the 2 pi I phi of x for some phi, some real value phi. And then if I write down what the definition of the Gowers norm is, so this product over the vertices of polar pi k, it's going to be e to the 2 pi I times some sort of a kth order derivative of phi. So phi of x minus phi of k plus 1. And this thing here is the kth order discrete derivative of phi. And so the Gowers norm can only be 1 if you've got this function phi on the integers whose kth order derivatives vanish. And it's well known that those are just exactly the polynomials of degree k minus 1 or less. So that's one observation.
N to be large enough comparably.
Yeah, so here I should say I'm always thinking of k as just fixed and n is always going to be large in Okay, so that's one observation. The second observation is that in the case when k equals 2, it's not too hard to satisfactorily resolve this inverse problem. If the U2 norm is at least delta, then f has a large Fourier coefficient, so it correlates with a linear phase. So there exists theta such that the normalized sum up to x, f of x, e to the minus 2 pi I theta x, is at least something like delta squared, so at least constant times delta squared. So that's a completely satisfactory solution to the inverse problem for the U2 norm. So why is case k equals 2 special? So this exploits a magic formula that the sum over parallel hybrids in dimension 2 is given by an L4 norm of the Fourier transform. So here I'm normalizing the Fourier transform, I mean the exponential sum. So I won't go through the details. This inverse theorem follows from that formula and an application of Parsifal's identity. But the key point is that there's a magic formula which very much depends on the orthogonality of characters, which is being used in the proof. The formula is very easy to prove once you write it down. Okay, so those I would call two sort of pretty basic observations. And then, given those, so this second statement, the inverse theorem for the U2 norm, it's a sort of robust version of the fact that the U2 norm is 1 if and only if f is a linear phase function. The U2 inverse theorem says the U2 norm is at least delta if and only if f correlates with a linear phase function. So perhaps the most obvious guess for what the general situation should be is that if the, let's say the U3 norm is at least delta, then f should correlate with a quadratic phase function. I've done this wrong already. I think I'm supposed to put that back in there. Right? So that would be the sort of naive guess for the inverse theorem for the high norms. So, naive guess, and it's really not that bad a guess in various different senses. It's actually true in finite fields. The guess would be that if the UK norm of a function is at least delta, then f has some correlation with a genuinely degree k-1 polynomial fate. So maybe let's not get as ambitious as polynomial correlation, but at least some bound below, depending only on delta. Some phi of degree k-1. Okay, so that would be the naive guess. And one thing that makes this theory quite interesting is that this turns out to be false. So this is false. And this is something that was sort of discovered in sort of related contexts by various different people. It was discovered in ergodic theory in a somewhat related context, and then it was also discovered by Gowers in more like this context. But yeah, it's false. There are exotic sort of degree k-1 objects which enter the picture, which are relevant, called nilsequences. Nilsequences. Okay. And they necessarily enter the picture. So let me now try and say what a nilsequence is. It's one of these definitions that's it's hard to give the full definition. It's a bit pointless, so I'll just give the key elements of it. And it's also very hard when I write down the definition to get any appreciation of what it says, which I'll hopefully try and make some more comments on as I go. So here's a rough definition minus some of the details. So this is the definition of a nilsequence. So the key structure is a nilpotent group. So G is a simply connected nilpotent Lie group. So it has some step S. Let me just write down something like the definition, then I'll give the canonical example. So what this means is that there's a kind of a series of subgroups terminating in the identity at the S plus first step, where this is the lower central series. So Gi plus 1 is the commutator of G with Gi. So the example to have in mind is always, I think, apart from the Abelian groups, which are maybe a bit misleading, the Heisenberg group of 3x3 upper triangular matrices is a simply connected nilpotent Lie group of step 2. So the commutator of this with itself is just things with 0 entries here and here, and then when you commutate another time, you get just the identity. So that's an object that one cannot avoid in this theory. And then inside there's a lattice. So the classic example would be in the Heisenberg, just the integer lattice. And then a nilsequence is something of the form f of g to the n, where f is a function on g mod gamma. Another way of thinking about this is f is a gamma automorphic function, so f of gamma x was f of x, and so f is a function of g. And the little g is an element of the little g in big G is some fixed element. So that's just sort of the bare definition of a nilsequence. And it has turned out that these are seemingly, well, they are a natural notion of what we call higher order character. They're very natural in terms of the higher degree Gowers norms. Let me write higher degree characters. And that's because of this key theorem called the inverse theorem of Gowers norms. So whilst I'm doing the border ratings, anybody got any questions on that?
Don't you impose any regularity on that?
Yes. So it's exactly. As thus described, I've basically just described an arbitrary sequence of, an almost arbitrary sequence of complex numbers. For it to be meaningful, you have to impose some regularity conditions on it. So I'll do that in just a second, without detail. Okay, so I'm now going to state sort of the main theorem in the subject, which is called the inverse theorem for the Gowers norms. Roughly speaking, it states that these nil sequences account for Gowers norms being large, but the version I'm going to state is a pretty new, as of last year, highly quantitative version due to Leng, Sa, and Sawney. So let me state that. So this is a pretty remarkable recent result in the area. So it's inverse theorem for the Gowers norms. Gowers norms with quasi-polynomial dependencies. So let me have a go at stating this theorem. Suppose that I've got a function as I've been talking about with a large Gowers norm. So at this point it's sort of hardwired into my head that I should change a k to an s plus 1. S is the step of the nilpotent group that's going to appear. So let S bigger than or equal to 1 be fixed. And suppose I've got that f is greater or equal to delta, where here is always f is some one-bounded function on 1 up to n. And the theorem is that f correlates with one of these nil sequences. Oops, sorry, I don't want a nil sequence just yet. So here's f. Let me make this an n. So it's like the naive guess at the top, except instead of a polynomial phase function, I've got this exotic thing called a nil sequence. Okay. So that was a theorem that was, as I've written it there, that's a theorem that was proven by Taran Ziegler and myself 15 years or so ago. But the remarkable thing that Leng, Sa, and Sawney have done is to make this highly quantitative. So here, okay, so the C sub S, it's not quite polynomial, but it's kind of almost polynomial. So these are called quasi-polynomials. So e to the minus log 1 over delta to the C. And, so as you remarked, there's all sorts of quantitative data associated with this nilpotent Lie group, and their theorem is that all of that quantitative data is also quasi-polynomial, or, in the case of the dimension, just logarithmic. So the dimension of the group, dimension of G, is just logarithmic. Again, these constants all depend on S. Dimension is logarithmic in 1 over delta, and various complexity parameters that I haven't defined So what are the complexity parameters? Well, I don't really want to go into this, but the most crucial one is kind of the smoothness of F. So for reasons that are basically my fault or me and Terry's fault, smoothness has traditionally been phrased in terms of the Lipschitz property, which is not really the right way to do things. Smoothness of F. But also the way that gamma sits inside G, the rationality of quantitative rationality of gamma. So these complexity parameters are also quasi-polynomial. Okay, so that's the theorem of Leng-Sansoni. I haven't defined these complexity issues carefully, of course, but the way one should think of this is it's an inverse theorem for the Gowers norms. That by itself would just be, there exists some function f and there exists some constant here, but they've done it with highly effective bounds. Okay. So this is a very impressive theorem. I didn't think I'd ever see this theorem proven. Just to give one example of how powerful it is, so let's give a couple of applications. So one thing they've done is they've improved Gowers bounds on Semiramis' theorem. On many progressions. But the more striking thing is that essentially, so this is a comment for people who know something about the work I did with Tau and Ziegler on linear equations in primes and those sorts of things. They've essentially removed any need for sieve theory in those things. So, remove the pseudo-random measures. From linear equations in primes. So it's kind of shocking. So where Tau and I would always, the first thing we would be trying to do when we're trying to understand primes is to first of all put them inside a sieve weight. So the primes sit inside a sieve weight with positive relative density, and the sieve weight is something you can try and understand. Essentially, Leng-Sansoni are just saying let's bound the characteristic function of the primes pointwise by 1. Kind of, because you can afford to lose the logarithmic density with these bounds that they have. So it's pretty shocking restructuring of the theory. Okay, so that is, any questions about the statement of this theorem? Yeah.
Is it easy to see if delta is 1 and small f has to be capital
Right, so when delta equals 1, that's a good question. So when delta equals 1, why does this include the polynomial example? So, yeah, small f will not be capital F. You can write these polynomial phases as a nil sequence on an appropriate, actually just on a torus. So in that case, the G will be, the way I've set things up, let's on a nilpotent Lie group. So no, the big F will not be the little f. I guess, yeah, the easiest way to illustrate that point would just be in the case of linear phases. So y is, so f of, so e to the 2 pi I d to n is equal to f of g to the n, where the g is just an abelian Lie group R, the gamma is equal to z, the little g is just theta, and the f of x is just the standard character e to the 2 pi I x. And because it's abelian, you wouldn't normally write g to the n, you'd normally write ng like that. So yeah, it's definitely not the case that the big F is the little f, even in the case delta equals 1. We have, yeah.
So can it remove more logarithmic densities?
Can it remove remove more than logarithmic density.
So you remove a log to...
Yeah, it's effective to sort of certainly arbitrary powers of logs and things. Okay, so I've stated this theorem, which I think is it's a remarkable black box that has already had loads of applications and will have more. So why am I not satisfied? I mean, I'm certainly impressed and quite happy about it, but what should we be looking for? Why should this not be regarded as a finished subject at this point? Okay, so what are the shortcomings of the situation as it currently is? Well, probably the main one is that currently the proof of this is approximately 200 pages long. So I'll maybe give a very brief overview on proof in a second. The proof itself, the paper in which they prove this, is 100 pages long, but they're importing ingredients from other work, as well as kind of quoting one or two bits from earlier work of me and Terry and Tammy. The thing they're importing from other work about the distribution of nil sequences is also not exactly self-contained. That also imports other things. So it's really a very deep and difficult theorem. Also, they're importing work of Tom Sanders, which they just quote. So using all sorts of, using many different ingredients. So I think it's pretty unsatisfactory to have a black box that's got a reasonably clean and natural statement, at least once you've thought about these things for a while. It's a statement that's forced upon you, yeah.
So I was wondering, how does this compare with this work of Manners? Was this something similar?
Yeah, so Manners proved a similar statement, but with quite significantly weaker bounds. So, for example, his bounds in the dimension were exponential, and his bounds in the correlation were doubly exponential. So, probably the biggest shortcoming is the nature of the proof, which is incredibly elaborate and uses lots of different ingredients. But then there are also some shortcomings, I think, in the statement of the result. So here are some weird things about the statement. So the most weird thing is, you've got to choose this G and gamma and F. So there are many nilpotent groups G. Even classifying nilpotent groups is a very messy business. So there are many G, gamma, and particularly F. Whereas you don't see that at all in the case of the U2 norm, where the only ones that really come up are these ones. So everybody knows these additive characters, e to the 2 pi x. I think if you've got R modulo z, and I say, it would be weird if I said take a Lipschitz function, whereas really I could just take e to the 2 pi I x. So it would be nice to know, so are there some natural class and in particular just a much smaller set. So are there some natural objects within this class? So that's one thing. Now, you can't try and answer that question by just sort of looking at the nil sequences for which the converse holds. So it's actually the case that for any nil sequence, so for any f, g, and gamma, if you correlate with a nil sequence, then you have large Gowers norm. So it is necessary to at least at some stage think about all of them, but there's maybe some natural way to refine that class. So the other thing that's not fully satisfactory about the statement, I mean, I'm asking for a lot here. They prove quasi-polynomial bounds, but really there should be polynomial bounds. Okay, not just quasi-polynomial. Not merely quasi-polynomial. And this is slightly connected with the first point, because I don't think, well, I know, that nobody's even really stated what the appropriate result should be. So what even is the statement? What would be a criterion for having a sort of correct statement? What would be nice is some statement that allows you to go from having a large Gowers norm to correlating with a nil sequence and then reversing that statement. So you'd like a statement that if you know this is true, then F had a large Gowers norm with only polynomial losses through this chain of reasoning. Okay, so if you apply this sort of thing to the lengths R Sawney, you get Gowers norm at least delta implies a quasi-polynomial with a nil sequence, and then there's a much easier argument that says if you have quasi-polynomial correlation with a nil sequence, you have a large Gowers norm. But in going through that chain of reasoning, you've obviously you've gone down to quasi-polynomial loss, not a polynomial loss. So that would be very nice to have. And one particular reason for wanting that is that it's essentially known to be, in the case of the U3 norm, so I'm slightly overstating this. We haven't, it's not quite been formulated exactly what, even in the U3 case, what this quasi-polynomial thing should mean, but it's basically equivalent to what's called the polynomial Freiman-Ruger conjecture in the integers. Which is an unsolved problem. So the polynomial Freiman-Ruger conjecture, so it's a statement about the precise structure of sets with small doubling constant in the integers. So that statement was proven in finite fields a year or two ago by Gowers and Manners and Tao and myself. But over the integers, it's still pretty much wide open, and that is essentially equivalent to polynomial bounds for the U3 inverse theorem. Okay, and then, so that's weird things about the statement. The proof, I've just sketched I just want to try and give you a very brief sketch of how complicated the proof is. It's very complicated, but I think, these nilpotent objects are pretty natural, and there really should be some way that explains why these come up. So where do the nilpotent objects come from, really? So they get constructed in the proof as it currently is in a very ad hoc and hands-on way, which I'll try and say a couple of things about. But yeah, I sort of feel that in mathematics, when you have a natural statement that's sort of forced upon you, like these nilpotent objects really do exist out there and they're clearly the things that are relevant in the theory, it's very unsatisfactory that the only proof we have constructs them in a highly ad hoc way. And obviously I suspect that there's some link between the above questions, so if one understands things properly, probably they should all be understood properly at the same time. just going to attempt to give like a 5-minute version of, just to try and give a sense of how complicated the proof is. Let's look at the U3 case. And the U3 case, that was actually mostly done by Terry and me 20 years ago. It's already way simpler than the higher order case. Sorry, yeah. So, yeah, the U2 case is already quite complicated and ad hoc. And is way simpler than the general case. Have I made it better or worse? We'll see how that goes. Okay, so I'm just going to write down a sort of rough chain of implications just to get a sense of how complicated this is. So you proceed by induction, and in the U3 case you proceed by induction from the U2 case, and in the U2 case there is a nice inverse theorem. So I'm going to greater than 1 means that bigger than some function depending only on delta. I'll put that into there. Or many h. Where delta sub h of f is a multiplicative theorem. So this is easy, this is almost just from the definition. So now if you put the U2 inverse theorem, you get that many of those derivatives have a large Fourier coefficient. So for many of those, for those derivatives that have a large U2 norm, they have a large Fourier coefficient, that's the U2 inverse theorem. So write this here. Then there's a magic argument of Gowers that says that those Fourier coefficients cannot vary arbitrarily in H. So phi has weak additive structure. And what that means is that so many h1 plus h2 equals h3 plus h4, so what we call additive quadruples, for which phi is respected. So phi respects that additive quadruple. Oops. Phi of h1 plus phi of h2 equals phi of h3 plus phi of h4. The way of formulating things you also need a small error, but that's so this is a kind of somewhat magical application of it's an argument of Gowers that uses the Cauchy-Schwarz inequality. But so then one needs to understand the structure of these somewhat additive functions, and that's related to things like Feynman's theorem. So the graph of such a function resembles a set with small doubling. But you need the strongest known quantitative forms of this, and this is work of Sanders, which already is pretty deep and uses stuff about almost periodicity. So phi agrees with phi tilde, and phi tilde is a linear function on a Bohr set.
I'm a little bit confused. I thought, maybe I misremembered, but I thought you said in the U2 case it's always correlating with a linear character. Or is it just set up in this way so it generalizes to higher U's?
This is true, and I've used that fact here. So this is that phi is the linear character.
But why do you need that? Isn't it obvious that it has next implication, or is that just it for the general induction argument?
Right, so this is the phase.
Yeah.
So each phi is a particular phase, and then this is a kind of correlation across the different phases for different h's. So each fixed h.
Yeah, okay, sorry, yeah, that makes sense. Yeah, thanks.
So phi agrees with a phi tilde, which is a linear map on a Bohr set. Okay, so a Bohr set is the set of, maybe I'll just say what this is. This is the set of integers where the characters with frequencies θ1 up to θd are all close to the identity, within 1/10 of the identity. I also won't say exactly what linear means. And so here, Sanders proved that D is quasi-polynomial, and that's the key. You really must have this to get the quasi-polynomial bound in the main theorem. This is somehow like the key place where quasi-polynomial inputs come in. Okay, so you've then got this weird linear object on a Bohr set. You then need to use classic geometry of numbers, like Minkowski type theorems, to basically say that that phi tilde, the only linear phases on a Bohr set are sort of the, quote, the obvious ones, which are going to be sort of θ1 times the fractional part of, so alpha 1 times the fractional part of θ1x, plus a genuine linear phase. So, yeah, those are the linear phases on a Bohr set. So then, going back to the first step, what you have is that the average, the sum over x and h, f of x plus h, times some sort of e to the 2 pi I of this kind of fractional part linear phase. So it's going to be, let me write it, let me pretend there's only one of those d's. So it's going to be something like fractional part alpha h. No, it actually doesn't make sense, does it? I need all of them. So you've got some weird statement that the derivatives of f correlate with, omitting the general linear terms. So the derivatives of f correlate with some bracket linear phases. Now, if the derivatives of something correlated with a linear phase, it's fairly easy to see that the something, the f, correlates with a quadratic phase. And you need a similar argument here, but quadratic phase gets replaced by bracket quadratic phase. So there's always these normalizations. So something like, it's different letters, so I'm going to use, let's say, let's use an N. And actually, let me just whiteboard, because this is quite an important line. One over n, sum over n, that's the big N, f of n, e to the 2 pi I, so alpha n, brackets beta n is large, or something like that. Okay, so that's a schematic of the sort of thing that you'd get. So you've gone from derivatives have bracket linear behavior to the function has bracket quadratic behavior. But this is not a straightforward step, because in the world of multidimensional maps, the derivative of a quadratic is a symmetric linear object. It's symmetric bilinear form. So there has to be some additional symmetry argument here. And then the final step, which is somehow the least satisfactory, illustrates what I meant when I said we're not seeing these nilpotent structures come in naturally. You then just, in an ad hoc manner, observe that this sort of a bracket linear thing can be constructed on the Heisenberg group. So I'll just show you how that works.
Isn't this something that Fürstenberg already observed?
Probably, yep. I'm not. the history of this is all sort of complicated. Yeah, I mean, it's Furstenberg, well, Konzer, Lessine, Furstenberg, and Weiss were the people who realized the relevance of nilpotent groups in the theory. So let me just show you how that last step works. So this is everything so far is kind of additive combinatorics, Fourier analysis, geometry of numbers, and so on. Nothing nilpotent's occurred. And then the nilpotent thing occurs at the very last stage, which is where you write down something like this sequence on the Heisenberg group. And then if you consider this modulo the integer lattice, so let's put A, B, C here to be integers. So if you want to reduce this to lie in the fundamental domain of the Heisenberg group modulo that integer lattice, you need to put an integer part of alpha n there to reduce this term to lie in the fundamental domain, an integer part of beta n there, and then you can kind of see that to reduce the top term to lie in the fundamental domain, you're going to get an brackets alpha n times beta n coming in here. So I don't know what it is exactly, but something like brackets alpha n beta n minus that. So from playing about on the Heisenberg group and reducing things modulo lattice to lie in the fundamental domain, you can start to see these bracket quadratics. And essentially what you do is you just play about with some suitable set of Heisenbergs to just visibly construct that object as coming from the Heisenberg groups. Okay, so that was a sketch of the U3 case. In the higher order case, it gets much, much worse. So you're inducting on the level of the Gowers norm, on the degree. But hidden in everything I said here, so in particular, hidden in here is this U2 inverse theorem, which was just Fourier analysis. And kind of Fourier analysis is bubbling just underneath the surface here. Whereas in the higher order case, you really need to understand how these higher order characters, these nilsequences, behave. So you don't have orthogonality relations for them. And you basically need to import the whole theory of that, which is a whole separate, fairly substantial body of work. So, I'm out of time, but hopefully that's giving you some impression of the fact that this key thing to take away perhaps is that the Lensar-Sawney result, this inverse over the Gowers norm, is like a fundamental black box in this area of additive combinatorics, in higher order Fourier analysis. But as things currently understand, one can have reason to hope that we won't forever have to live with this enormously complicated proof. Maybe there's a better way to do things. And hopefully that would also lead to a more natural formulation, which potentially could also have applications, for example, to polynomial Feynman-Ridger over Z. Okay, so I'll stop there.